Good morning, gentlemen. Today is Cinco de Mayo. So um, take a nice big jar of Hellman's or maybe Miracle Whip, whichever you prefer. Put it in the sink and you'll have Cinco de Mayo. All right. Anyway, uh, so today we're going to continue with our discussion of waves. And of course, I think I'm on the wrong slide. So that's okay. We'll fix that in just a second. So we had waves, types of waves. Oh, actually, this all the stuff that we talked about in yesterday's lesson is actually today going to be available for you or with you to you in a video that I found. So in the second slide here in today's video, there is a link to a video that I found on the characteristics of waves. It doesn't really help with today's lesson, but it's a nice little summary of what we talked about in yesterday's lesson. All right, so keep that in mind. So today we're going to talk about the behavior of waves at boundaries. In other words, when a wave strikes the boundary between one medium and another, like an ocean wave hitting the beach, okay, or a sound wave hitting a wall, right, traveling through the air and then eventually hitting the wall, or a light wave striking a window. All right, rays of light are actually changed when they pass through glass. All right, what happens here? How do the waves themselves behave? All right, so in order to talk about that, the first thing well, before we get into that, I do want to point out that there's going to be a video here. Now, I'm going to have to post this PowerPoint again so that you can, I don't think that you're going to be able to stop my video to start another video, but if you copy the link here and plug it into your browser, you should come to the YouTube video. And it's a nice little summary of the things that we talked about yesterday. So let's get into what we really need to talk about today, which is waves at boundaries. What happens when a wave reaches a boundary? Right, well, there's a lot of writing in this thing, so I'm going to encourage you to pause the slide and write down the notes and do whatever you need to do in order to get all this information down. But here, whenever a wave reaches a boundary between two media, now media are just different substances. It can be air and water, or air and a wall, sheetrock. It can be water and sand. It can be, whatever the two media that are carrying this wave happen to be. So whenever a wave reaches a boundary between two media, part of it will be reflected, meaning bounced back. And of course, if you look in a mirror, that's obviously light rays, which are waves, reflecting back onto or into your eyes. All right, and depending upon where those light rays are originating from, you see different parts of your face or your body or whatever it happens to be. We'll talk more about images produced by a mirror and lenses and stuff when we get into a specific discussion of light. But that's what reflection is, when the sound wave bounces back or the light wave bounces back. But part of that wave will also be transmitted. In other words, some of the energy of the wave goes into the second medium. So sound is absorbed by the wall. If a wall is very smooth and there's no carpet, like, for example, in the room that I'm in now, there tends to be a little bit of echoing going on. All right, if I was to put a carpet down on the rug here, that would absorb a great deal of the sound because it's a rougher substance. Anyway, so part of the medium part of the wave is reflected and part is transmitted. And the fraction depends on the difference in rigidity between the two media. In other words, which one's more dense or solid or that sort of thing. Okay. So what actually then happens when we get to a boundary? Well, there's three possible scenarios here, all right, in terms of the differences between the two different media that the wave is traveling through. In the first case, um, you've got a situation where you've got a less rigid medium going into a more rigid medium. And of course, if we were in our classroom right now, I would have that big old spring stretched out across the classroom, and I would show you that when I sent the wave down, right, I've got my little baby slinky here, but when I send the wave down, it bounces back, and that's eventually causes the whole thing to kind of wiggle. All right. Um, but most of the wave is reflected. Now, when you travel between two media that have similar densities, like a spring to a different spring, and in this case, I would simply attach two slinkies to one another, you'll find that about half of the wave is reflected, but the other half is transmitted. It's about a 50-50 split. If you go from a more dense medium to a less dense medium, like a spring to the air, most of the wave is reflected. And so you can do that. If you've got a slinky at home, all right, if you take this slinky and you um, do that, you'll see that most of the wave goes right back up and it just keeps moving. Right? It's hard to, I know it's hard to see, but the wave bounces back. It comes right back up. Doesn't lose a whole lot of energy there. So the moral of the story here is the behavior of the wave depends on the difference in densities between the two media that we're moving between. Now, the other thing that's interesting about this is that if medium B is more rigid than medium A, whoops, the reflected wave will be inverted. And so that would, oh, come on, that would be this case where the wall is more rigid than the air, than the spring rather. And so the reflected wave will be inverted. Now I'll show you what that looks like in the next slide. On the other hand, if medium A is more rigid than medium B, then the reflected wave will be in phase. And that would be shown here, spring to the air. All right, the first medium, the spring, is more rigid than the second medium, the air. Now, let me see if I can actually get the drawings done here the right way. So let's say, for the sake of argument, that this is my hand over here, and I'm generating a sine curve, a transverse wave. And there's a boundary right there. And I'm going to try just pretend that's a perfectly vertical line. And so what happens is that if this is, let's say, air, or this represents a spring, and this is the wall, most of the wave is going to be reflected, but it's going to be out of phase. Now, this is going to be tough for me to draw. I'm actually going to start it at this side. All right, and it's going to look like this. I'm not doing a very good job with the amplitude. This is really tough to do with a mouse. All right, but whereas this part of the wave is moving in this direction, this part of the wave is moving in this direction. So the black is moving toward the right, and the red is moving toward the left. And so in this case, less rigid to more rigid, the reflected wave is 180 degrees, what we call out of phase. It's tough to write with this thing too. All right. Now, in the middle version, what you'll find is that if this is a spring and there's another spring over here, so spring to spring now, the part of the wave will continue. Oh my goodness. Part of the wave will continue, but it will be a smaller amplitude. And I know I'm not doing a great job with this, but a smaller amplitude. Part of the wave will be reflected. I don't think I didn't, the right-hand side is not great, but this one's better. all right, like so, all right. It's not a great diagram, but you can see the idea. And again, the black is moving toward the right, and the red is moving toward the left. Now, if you went from a spring to the air, interestingly enough, most of the wave will again be reflected, but this time it's going to be reflected along the same path. I'm not going to draw over the top, but just so that you can see it goes in the same direction. Whoops, ow. I hit a knob on my desk. So anyway, in this case, again, most is reflected. And in this case, we call this one in phase. All right, this is a wave that is in phase. Okay. So again, less rigid to more rigid, equal rigidities, more rigid to less rigid. Okay, and that's the examples that you see here. All right. So when you've got a big difference in rigidities, the wave is mostly reflected. When the rigidities are similar, it's about 50-50 transmission to reflection. And if you go from less rigid to more rigid, it bounces back 180 degrees out of phase. If you go more rigid to less rigid, it bounces back in phase. Okay, so that brings us to our next little discussion here. What happens to the other properties of the wave, not just the direction up or down that it's bouncing, but what happens to the actual wave properties, the frequency, the velocity, that kind of stuff. All right. Again, this is a lot of writing here, but keep in mind, although the speed of a wave in a given medium is constant, so every wave in the ocean is moving at a constant speed. All right. It does vary a little bit depending on salt concentration and that sort of thing. So, but it's pretty close. But although the speed of a wave in a given medium is a constant, when the wave passes into a new medium, its velocity will change. So the speed of sound in dirt is different than the speed of sound in air. The speed of light in water is different than the speed of light in air. So since the wave in the new medium is generated directly by the wave in the old medium, the frequency in the new medium is the same as in the old. So let's say this is the boundary between a road and sand. You're driving along the beach in your jalopy, okay? And so here you are, doopy-doo. I'm looking at it from the top. Here's the 4 tires of the jalopy, okay? But for some reason, you come down and just this tire right here, the one on the passenger side, so you're moving this way, but the one on the passenger side hits here. And so now your car is kind of at an angle. All right, so you got that tire, that tire, that tire, and that tire. Now, what happens to the tire when it hits the sand? Is it going to be able to travel at the same speed that it's traveling along asphalt? And the answer is no. All right, what's going to happen is that front passenger side tire is going to slow down, but the rest of the tires are still going to be trying to continue at least at the same speed. And so what happens is the entire car is going to change direction. I'm not doing a very good job drawing my car, but now it's going this way, whereas here it was going this way. All right, because that front tire caught and got turned. Okay, now this is very easy to show in your bathtub. All right, so tonight, boys and girls, when you go up to take your bath, all right, I want you to play in the water a little bit and watch the waves. All right. If you were to take a piece of wood or your rubber ducky and put it at one position and have the waves go around it or past it, you'll see that they change direction, right? And we'll get to that in a little bit. Hopefully I'll be able to find some good YouTube videos to demonstrate this stuff. But let's say that this is the boundary between two different media. And I'm going to draw a wave front, all right? So a series of waves. And so they're all parallel, and they're all moving toward the right. And I'm trying to draw these all the same distance apart, which is quite the challenge. All right, but this wave front is moving this way. All right, that's the direction of the wave front. Now, it hits the boundary between the two different media, and it will change its direction because now it's going to travel more slowly. And so when it hits here, whoops, that one wasn't very straight. Okay, now, two things. First, whoops, this wave is now moving in this direction. And although this is a very rough sketch, I'm hopeful that you can see that the wave, and again, you're looking at it from the top, right? So you're, a seagull flying along above this thing, looking down. Hopefully you can see that the wave has changed direction, right, between the red medium on the top and the green medium on the bottom. But not only has the direction changed, but now look at the distance between here and here. All right, that is one wavelength. But now look at the distance between, it's not a good place, but right there. Now this is the new wavelength, okay? And so the wavelength has changed. And we know the speed has changed. And because V equals the frequency times the wavelength, all right? If the wavelength gets smaller, then the velocity must get bigger. Okay, and so I'm sorry, it gets smaller as well, right? Because they're directly proportional. Okay, so if the velocity decreases, the wavelength decreases. If the velocity increases, then the wavelength increases as well. Okay. All right. So that is that for that today. All right. There is no homework assignment due for today. So happy Cinco de Mayo, and I will see you tomorrow. Have a great day.